Assalamu alaikum. I'm Faculty002, affiliated with the Department of Physics at the Kust University of Science and Technology in Pakistan. This video is recorded as part of an undergraduate course offered at the Kust University of Science and Technology, that is Phy213 Fluid Mechanics. And this lecture will be discussing compressibility of fluids. By the end of this lecture, you will be able to appreciate the basic concepts involved in the compression and expansion of fluids. You will be able to model or predict the variations in volume as a function of temperature and pressure, or variation in the density as a function of temperature and pressure of a known fluids in terms of its standard tabulated properties. That would mean the coefficients of compression and expansion, both at the constant temperature and constant pressure. You will also be able to calculate the coefficients, that's the compression and expansion, of an unknown fluid from the experimentally observed values of volume as a function of temperature and pressure. We follow the fourth edition of Fundamentals and Applications of Fluid Mechanics by Yunus Angel and John Simbola, published by the McGraw-Hill. There are many other books available in the market that one could refer to. Four such books are shown over here. The outlines of this talk are as follow. We'll have a brief recap of the previous lecture, and then we'll have a slide about the basics from solid mechanics. We'll talk about the compression and expansion of fluids. We'll have discussion about the coefficient of compressibility, that's the bulk modulus. We'll talk about the isothermal compressibility, and we'll have a discussion about the coefficient of volume expansion. Let us recap what we discussed during the last lecture. We learned that the total energy of a fluid is the sum of microscopic and macroscopic energy. We learned that the microscopic energy for a stationary fluid is its internal energy U. We also learned that the microscopic energy for a moving fluid is enthalpy, denoted by H, which is equal to the internal energy plus the PV energy. The macroscopic energy is related to the motion or external influences such as gravity, electric field, magnetic field, surface tension, etc. The change in the internal energy could be written down as the specific heat at constant volume and the change in temperature, and the change in enthalpy could be written down as the specific heat at constant pressure and the change in the temperature. For incompressible fluids, we learned that the change in an enthalpy is equal to the change in the internal energy plus the change in pressure over the density. Some school physics. We have a term stress that is defined as the force per unit area. Consider a solid cylinder having length L and cross-sectional area A. When a force F is applied in a direction as shown over here, then this force will cause a reduction in the length of the cylinder by an amount delta L. If a force is applied in a direction as shown over here now, this force will cause an increase in the length of the cylinder by an amount delta L. Stress could be tensile in nature. Tensile stress is something similar what we have shown over here, and it causes a change in the length, or it changes the dimension along which the force is applied. Stress could be shear in nature, which is very important in fluid mechanics, where a force is applied not normal to the surface but the force is applied tangential to the surface area. We have another term, strain, which is defined as the change in the length delta L over the total length L of the object. We have an important law, Hooke's law, which states that the stress is directly proportional to the strain, where the constant of proportionality Y is known as the Young's modulus or modulus of elasticity. In other words, one could write Young's modulus Y as the ratio of the stress and strain. Fluids behave differently than the solid under the influence of a force or pressure. In case of solids, when a force is applied along a dimension, that will tend to produce changes along the same dimension or the same direction. Whereas in case of fluids, when a pressure is applied onto a body of fluid, it is distributed uniformly throughout the body of the fluid. Fluids could be expanded through two different means. Either you increase or decrease the temperature while keeping the pressure constant, or you increase or decrease the pressure while keeping the temperature constant. The process in which you keep the temperature constant is referred to as isothermal compression or expansion, and the process where you keep the pressure constant is referred to as isobaric compression or expansion. In isothermal compression and expansion, you have a fluid body at certain temperature T, and the pressure applied from all direction is the same as P1. Then when you increase the pressure from P1 to P2 while keeping the temperature as constant T, that will tend to reduce the volume of the fluid or increase the density of the fluid. So you have a variation in the volume as a function of variation in pressure at constant temperature, or you could say that you have a variation in the density of the fluid as a function of pressure at constant temperature. When you increase the pressure, that will result into a decrease in the volume. Consequently, you will have an increase in the density of the fluid. When you decrease the pressure at constant temperature, that will result into an increase in the volume of the fluid, and consequently you will have a decrease in the density of the fluid. At constant pressure, that is the isobaric expansion or compression, you have a fluid body which is at certain pressure P and temperature T1. When you increase the temperature from T1 to T2 while keeping the pressure constant as P, you have basically increased the volume from certain initial value V1 to V2. So you have an increase in the volume by an amount delta V. See, when you talk about the variation in the volume as a function of variation in the temperature at constant P, that simply means that you're talking about the variation in the density as a function of temperature at constant P. When you increase the temperature, that would result into an increase in the volume, and that consequently means that you have reduced the density. When you reduce the temperature, that will result into reduction in the volume, and consequently you will have an increase in the density of the fluid. So any incremental change in pressure or temperature results in a change in the volume of the fluid. Compressibility of fluids at constant temperature, that is the isothermal compressibility of fluids. In case of solids, we had Young modulus, which was defined as the ratio of stress and linear strain. Uh, in case of fluids, we will have bulk modulus now, which is the ratio of compressive stress over volumetric strain. The compressive stress is simply the change in pressure, that is the del P, and the volumetric strain is the change in volume uh, minus del V over volume V. Take care of this minus, because that simply means that if you increase the pressure, you are reducing the volume. If we denote this bulk modulus by kappa and using these definitions, we have the variations in pressure with the variation in volume per unit volume. Rearranging this equation, we have kappa is equal to minus V, which is the volume, and del P or del V at constant T, which is the temperature. The coefficient of compressibility is also known as bulk modulus of compressibility or bulk modulus of elasticity. Reproducing it here from the last slide, we have kappa is equal to minus V del P over delta V at constant T. If we look at the dimension here, we have volume dimension in the numerator, and we have the volume dimension in the denominator. That would mean that kappa will have the dimension of pressure. So the unit we use will be the unit of pressure for the coefficient of compressibility. In terms of the specific volume, we can write down density is equal to 1 over V. That would mean that d rho or dV is equal to minus 1 over V squared. And rearranging, we will get d rho over rho is equal to minus dV over V. If we use the d rho or rho value as equal to minus dV over V and put it into the equation over here, we can write down kappa in terms of rho. So kappa is equal to rho del P over del rho at constant T. In terms of finite changes, we can rewrite this kappa is approximately equal to minus delta P over delta V over V. Or we can write this down as delta P over delta rho over rho. And all this, of course, we have it at constant temperature. So change in pressure corresponding to the frictional change in the volume or the frictional change in the density while keeping the temperature constant. And that's the definition of coefficient of compressibility. So let me say it again. The coefficient of compressibility is the change in pressure corresponding to the frictional change in volume and density at constant temperature. For truly incompressible fluid, the volume does not vary with pressure. That would mean that you have delta V is equal to 0. Putting delta V is equal to 0 into this relation would mean that kappa is equal to infinity. So large kappa therefore means large change of pressure for a small change in volume. For example, when you have 1% of compression of water at standard temperature and pressure, that would require 210 atmospheric pressure. And putting these values would make kappa equal to 21,000 is a huge value for kappa. While closing the faucet of your washroom, some of you might have noticed or heard a very freaking sound having a resemblance with the water pipe being hammered. This phenomenon is known as water hammer phenomenon. Is caused by a local compression due to the sudden restriction in the fluid flow because of the closure of the wall, or a sort of shock waves are produced along the pipeline. These shock waves can have a very damaging effect on the pipeline and can potentially rupture the pipeline. In order to overcome the damaging effect of this water hammer phenomenon on the pipeline, a surge tower is usually deployed that has an open surface in the tower that works as a shock absorber. On a smaller scale, usually a hammer arrestor is installed that takes care of the water hammer phenomenon. Coefficient of compressibility for an ideal gas, we know that P is equal to rho or T for an ideal gas, where rho, remember, is the inverse of the specific volume. If we write down the changes in the pressure with respect to the change in density at constant temperature, from this relation we can write this down as RT. And we also can write down from this relation that RT is equal to P over rho. So that would mean that we can write this down, that the variation in the pressure with the variation in density at constant temperature is equal to P over rho. Or using the coefficient of compressibility kappa from the earlier slide, we have kappa for an ideal gas is equal to the pressure P. So the coefficient of compressibility of an ideal gas is equal to its absolute pressure. Therefore, for an ideal gas at constant temperature, we have kappa is equal to absolute pressure P, and kappa is approximately equal to the variation in the pressure. These are finite variation in the pressure over the finite variation in the density per unit density. Using these relation for the kappa, we can write down the variation, the finite variation in the pressure per unit pressure is equal to the finite variation in the density per unit density, or the frictional change in pressure is equal to the frictional change in the density of the fluid. This shows that the percent increase in the density of an ideal gas during isothermal compression is equal to the percent increase in the pressure of the fluid. Let us calculate the increase in pressure for the corresponding 1% decrease in volume of air at the absolute pressure of number 1 atmospheric and number 2 1000 atmospheric. We are given that the fluid is air and the pressure is 1 atmospheric, and the frictional change in volume delta V over V with the negative sign is equal to 0.01. We assume the air to be an ideal gas, and from the compressibility of an ideal gas we have delta P over P is approximately equal to delta rho over rho, which is equal to minus delta V over V. Or we can write down delta P is approximately equal to minus delta V over V into P. If we put the values from the data given, we have delta P is approximately equal to 0.01 multiplied by 1, which is equal to 0.01 atmospheric. This is a very small pressure required in order to decrease the volume of a gas by 1% at 1 atmospheric pressure. Now let us see how much pressure would be required in order to have the same 1% decrease in the volume of the air at 1000 atmospheric. Once again, the given data is pressure is 1000 atmospheric and the fluid is air, and the frictional change in volume is 0.01. Using equation 1 from the earlier slide, we have delta P is approximately equal to minus delta V over V into P. Putting the values from the data, we get 0.01 into 1000 is approximately equal to delta P, which is equal to 10 atmospheric. Now this pressure variation is a lot more then the change in pressure required in case the initial pressure was 1 atmospheric. For the same fractional change in volume, the variation in pressure is different for the two cases. The fractional change in volume or density corresponding to a unit change in pressure at constant temperature represents the isothermal compressibility denoted by alpha. It is defined as the inverse of the coefficient of compressibility kappa. We used the definition of kappa from the earlier slides. We have alpha is equal to 1 over kappa, which is equal to minus 1 over V del V over del P at constant T, or we can write this down as equal to 1 over rho del rho over del P at constant T. The units, because the dimension of rho in the denominator and the del rho in the numerator will cancel, so we have the dimension of alpha is 1 over pressure, so the units of alpha is 1 over Pascal. Recap, and this about the isothermal compressibility. We have the coefficient of compressibility defined as kappa is equal to minus V del P over del V at constant T, and that could be written as rho del P over del rho at constant T. For finite change, we have kappa is approximately equal to minus delta P over delta V over V, and that could be written as delta P over delta rho over rho. And remember, for an ideal gas, kappa for an ideal gas was equal to the absolute pressure P, or we could write down delta P over P is equal to delta rho over rho. Isothermal compressibility defined as alpha is equal to inverse of the coefficient of isothermal compressibility, which is equal to minus 1 over V del V over del P at constant T, which is equal to 1 over rho del rho over del P at constant T. The density of a fluid depends strongly on the temperature and weakly on the pressure. In isobaric processes, we look into the variation of density as a function of temperature at constant pressure. As an example, look at the rise of hot air near the surface of the earth because of the variation in the absorption of sunlight. You could have different regions or different pockets of air near the surface. Some pockets will have a temperature lower compared to another pocket where the temperature is higher. In the region or pockets where the temperature is lower, you will have the density higher than the region or pockets where the temperature is higher. Because of the gravity, the cold region will sink towards the surface of the earth and spreads around the surface of the earth. This will provide a buoyant force that will float the hot air up. Some examples of volume expansion. Hot air balloon is a very distinct example of volume expansion. The balloon is positioned in a manner to catch the air being heated below. The hot air fills the balloon as buoyant force lifts the hot air balloon high into the sky. Chimney is another example where the volume expansion is employed for the exhaust of the smoke. Wind is another example where the expansion of fluid because of the thermal changes is used. Ocean current is yet another example of volume expansion because of the variation in the temperature at constant pressure. The coefficient of volume expansion beta is defined in terms of the variation in volume as a function of variation in temperature at constant pressure. Beta is equal to 1 over V del V over del T at constant P. This can be written down as minus 1 over rho into del rho or del T at constant P. You may have noticed something here, that the expression in terms of density has a negative sign here, while the expression in terms of the volume does not have a negative sign, is contrary to what we had in the isothermal compressibility case. In case of isothermal compressibility, remember, we had a negative sign here or a positive sign here. The reason being that in this case here, when you increase the temperature, the volume also increases, so you have a positive sign. When you increase the temperature, the density decreases, so you have a negative sign. The dimension of beta is the inverse dimension of the temperature. The reason being the dimension in the denominator for density will cancel with the dimension of the density in the numerator, or the dimension of the volume in the denominator will cancel with the dimension of volume in the numerator. We can write down beta in terms of the finite differences as beta is approximately equal to delta V over V divided by delta T, and that's equal to minus delta rho over rho divided by delta T, and all this is done at constant pressure. Consider the case of a fluid at 295 degree Kelvin and 10 power 5 degree Pascal having a mass of 1 kg. By changing the temperature to 296 degree Kelvin while keeping the pressure constant, one can observe a change in the volume. The change in volume is given by del V over del T at constant P divided by multiplied by the total finite difference in the temperature. Similarly, when you have another fluid at 295 degree Kelvin at 10 power 5 Pascal and 1 kg, by changing the temperature from 295 to 296 degree Kelvin, and here you can see that the change in volume is very small compared to the change we had before. Now the case over here is the large beta case, where the later case here is the small beta case. Let's look at the coefficient of volume expression beta for an ideal gas. We had beta is equal to minus 1 over rho over del T at constant P. For an ideal gas, we have P is equal to rho RT. We can write this down as rho is P over RT, or we can write down del rho over del T is equal to minus P over RT squared. We can write this down as minus 1 over rho over del T at constant P is 1 over T. Putting this value back into the equation for coefficient of volume expansion, we get that beta is equal to 1 over T for an ideal gas, where 1 over K is the unit for the beta over here, and T is the absolute temperature. In case of natural convection, because you don't want to be influenced by the region outside, so the outside region is taken very remote, and we consider this to be at infinity. So the beta terms could be defined in terms of rho subscript infinity minus rho over rho divided by T infinity minus T. And this we can write this down in terms of rho infinity minus rho is equal to rho beta into T minus T infinity. So larger the difference in the temperature, larger will be the difference in the volume, or the difference in the density that one would encounter, and that means larger buoyancy force, and larger buoyancy force means stronger convection current, and that implies higher Q rate. Let's recap. We have volume expansion beta is equal to 1 over V without a negative sign into del V over del T at constant P, which is equal to minus 1 over rho over del T at constant P, and the units are 1 over T. Finite changes, we have beta is equal to delta V over V delta T is equal to minus delta rho over delta T. And for an ideal gas, we know that beta is equal to the inverse of the absolute temperature. Of course, all these are at constant pressure. And for the natural convection, we have rho infinity minus rho is equal to rho beta into T minus T. Now, when we vary the temperature and pressure simultaneously, we have the V volume as a function of temperature and pressure. We can write down the total change in the volume, or total variation in the volume, is equal to the change in the volume as a function of change in the temperature, and the change in the volume is a function of change in the pressure. So adding the two changes together, we get the total change in volume. So dV is equal to del V over del T at constant P into dt plus del V over del P at constant T into dP. We have a definition of alpha is equal to minus 1 over V del V over del P at constant T, and beta is equal to 1 over V del V over del T at constant P. Putting these values into the relation over here, we get dV is equal to beta dt minus alpha dP into the volume V. Or in terms of finite difference, we can write this down as delta V over V is equal to minus delta rho over rho, approximately equal to beta delta T minus alpha delta P. I thank you for watching and listening. Thank you.